Assalamu alaikum students. So today we will start with the new paper 6, May-June 2023, first variant. So question 1 says, ethanol can be made by fermentation of sugars found in the plants. A byproduct of the fermentation is carbon dioxide. A student made some ethanol using the following method, and these are the steps. After going through the steps, we can move on to the question. Question A says, name the item of the apparatus labeled A in figure 1.1. So in figure 1.1, the apparatus labeled A, as you can see, it is basically the conical flask. So you will write here, conical. So it is conical flask. Then part B, explain why hot water rather than cold water is used in step 2. So basically in step 2, it was meant to remove the sugar out of the sugar cane. So the only way we can do this is to take out the sugar by dissolving the sugar cane in the hot water. So we would say the sugar dissolves faster. That's why, because cold water and as any other liquid in the cold situation cannot dissolve other substances to a greater extent. That's why. Then part C says, name the method used to remove the solids from the mixture in step 3 and draw a diagram to show how this is done. So in the step 3, we have to remove the solid from the mixture, and mixture is basically in the liquid form. So the only way we can remove solid and liquid from each other is through the filtration method. So we will apply the filtration here. So we write filtration under this question. Filtration is a process name and the diagram. If you remember, we need a conical funnel for this purpose. A conical funnel is something like this. It's a Y-shaped, and then there is a long neck at the base of that conical funnel. And we also require a filter paper for the we also require filter paper for the filtration purpose. So that can only be adjusted in the conical funnel. So I will draw another line here that is representing a filter paper is placed inside the mouth of the conical funnel. So this diagram is showing both the conical funnel as well as filter paper. Then D says, state why the sugar solution is allowed to cool before the yeast is added in step 4. Okay, we have to cool down the sugar so that the yeast can then be added. The yeast, if you remember, we studied in the literature, it's a microorganism. So microorganism cannot survive in the hot water. In the previous step, in the second B step, we added the hot water. The hot water can be of a temperature above 60, 70, 80 degrees centigrade. It can be a temperature lying within this range. So in this temperature range, the yeast cannot properly work. We can say it will die. So another thing, we are applying the fermentation method here. And we remember from the literature that fermentation occurs between the temperature of 25 degrees centigrade to 35 degrees centigrade. Because in this temperature range, range the yeast can work properly. So we will write that fermentation occurs between the 25 degrees centigrade to 35 degrees centigrade, or the enzyme which we are using here, it is also a yeast. It is also the yeast is also the enzyme here. Enzyme are biocatalysts. So if you do not use this temperature range, we can say the enzymes are denatured. They are denatured at high temperatures. Then next part is E. Describe how the appearance of lime water changes as fermentation takes place. So if we go back over here, during the fermentation of the sugars, we remember there is a formation of the carbon dioxide. If you remember the equation C6H12O6, if it goes through the fermentation method, it produces a carbon dioxide plus water. Now this carbon dioxide gas, when reactive with the lime water, we remember the composition of lime water is calcium hydroxide, CaOH 2 whole twice, CaOH whole twice. So when it reacts with carbon dioxide, it produces the calcium carbonate. It produces calcium carbonate, CaCO3, which appears as white precipitate, and uh, the solution exhibits as lime water. So it appears as milky. It appears milky. The calcium hydroxide is actually colorless. Lime water is a colorless, but white precipitate appears like a milky solution. So you will write over here, describe how the appearance of lime water changes. We will write it turns from colorless to milky. Then F says, describe how the student could tell the fermentation is complete. Okay, as we said that the carbon dioxide is being liberated out of the reaction by the reaction of the fermentation. Carbon dioxide is coming out from here, from the solution. It's coming out, moving upward into the delivery tube. So that is happening somewhere in this flask. It is happening inside of this conical flask. So conical flask is producing the carbon dioxide. We can only tell that the reaction is complete if the carbon dioxide formation stops here. We do not see any more bubbles coming out of the liquid. That indicates the carbon dioxide has stopped forming. So we will write over here. There are no more bubbles. There are no more bubbles in the setup, or also the same can be applied over here, because the carbon dioxide is going into the uh, lime water solution as well. That end of that delivery tube is dipped into the liquid. It is dipped into the liquid. So if you just replace this test tube with another lime water and it does not uh, turns milky, or there are no bubbles formed in the test tube, we can tell that the reaction has stopped. So you will write, there are No more bubbles produced. Then G is name the process used to separate ethanol from the mixture obtained by fermentation. Okay, over here, if we come back, so as we were saying that the the carbon dioxide is coming out from the tube. All right, so carbon dioxide is moving into the delivery tube and into the test tube. Then how do we separate the water that is produced inside this conical flask? Separate this carbon dioxide with that of the ethanol, which is also present inside the same flask. So both of them are present, the water and the ethanol, both are present inside the flask. So to separate them from each other, we remember the process of the this fractional distillation. The same method which we applied to separate the fractions of the petroleum, it's the name. It's the name. It's not the setup, it's the name of the process. So we will apply the same procedure here. It is also applied to remove the gases from the air. The different component of the air are also separated by using the fractional distillation. So in this way, we have finished the first question. Now we move on to the next question, question number 2. Student investigates. I will just move on to the part of answering because you can read the question by yourself. It says just fill up the table by proper reading. So experiment 1 and final bureau reading. Experiment 1 final bureau reading, which is over here. So I need to zoom it. This one. Final bureau reading. So if it is 18 centimeter cube, this one is 18.1, 18.2, and this one is 18.3 cm cube. So this will be our result, 18.3 for the final bureau reading, 18.3 cm cube. And then the initial bureau reading of the experiment 1, initial bureau reading, and so let's check it. So we can see this is 1, 2, 3, 4, 5, 6. So 0.6 cm cube. It is 0 point, oh, sorry, not there, over here. It is 0.6 cm cube. And then next is experiment number 2. So for experiment 2, initial value is 9.2. We can see it. It is 9.2 over here, 9.1, 9.2. And the other value, which is the initial reading, final reading, it is clearly 21 cm cube. But we will need to put decimal point as well. So experiment number 2, the initial value is, we need to write the final beauty rating first. So the final beauty rating will be 21.0 cm cube. Do not forget to put the decimal point here because we have been using the one decimal point in all the readings. So we need to put one decimal point over here as well. So it is 21.0 cm cube, and the initial value was 9.2 cm cube. Then we have to find the titer. It says titer. Titer is basically the difference or added amount. Added amount also means a titer. It is the difference between the final value minus initial value of the volumes. If we find the difference, we get the volume of the added. So the difference of the first will give you can calculate it by the calculator. So it shall give you 17.7 cm cube. One more thing. You do not need to write cm cube every time because we remember it is already given in the statement or the heading of the question. It's already in the table over here. So you do not need to put cm cube for the values. Was 0.6. So 17.7 is the result over here. And in the second experiment, it is 11.8. Okay. Then it says, explain why a white tile is used during the titration. So if we look at the procedure, it said that we had to use a white tile just below the burette. Now the reason behind this. The white tile has not been mentioned in the statement, but if you have ever experience of performing the titration experiment in the lab, you should remember that whenever a reaction is happening, there is a formation of some color change. The beer, the conical flask, which is placed below the burette, it shows some formation of the color change here, or it could also have the formation of some sort of precipitates. So these color changes or these precipitate formation is more visible if we use a white tile below the if we have the white tile as a base on which the stand or the burette is placed. The flask is placed on the white tile and then the burette is just above it. This is the burette portion. So that's why we use a white tile here. We will write here to make a solid or precipitate is visible clearly, and then we can also raise the other is to make color change easier to see or easily visible, easily visible or easier to see. That's why. Then C part says in experiment 2, the burette and the cauliflower are both rinsed with water. The burette is then rinsed with solution B. State why both the burette and the cauliflower are rinsed with water. So if we remember, the experiment 1 was being conducted using the solution A. But in experiment 2, we had to use the solution B instead of the solution A. So we remember both A and B are basically different solutions of the copper sulfate having different amounts present in them. So that difference in the amounts of the copper sulfates can affect our results. So we can say that we will be using the distilled water to clean the solution A. Clean means remove the solution of the experiment 1. Second says clear why the burette is then rinsed with solution B. Okay, so in solution B we have a different concentration. That difference of the solution before doing that we use the water. The same apparatus, which in our case is the burette and the conical flask, both of them. Basically, we added the solution A and B in the conical flask. So conical flask would have some amount of the water present during the rinsing. Burette and conical flask both had some sort of the water present. These were in the form of the droplets. Droplets of the water were there. That droplets of water can also affect your results. Affect the results. So to prevent that difference in the result, we have to remove the water, and that is done by using the rinsing with the solution. Like the same solution is put into the burette and the conical flask, and it is swirled and then discarded. You pour the solution, you swirl it, and then you discard it. This is called rinsing by the solution. So we will say to remove water. Then third part, describe how the result of experiment 2 would be different if the conical flask is rinsed with aqueous ammonia after rinsing with water. Okay, it says that if you rinse a conical flask with the ammonia after it was rinsed with water, so basically we remember that we had to pour exactly 25 cm cube of the ammonia using the measuring cylinder. Using it, we had to pour only 25 cm cube. What if we rinse the ammonia? If we rinse with ammonia before doing the titration, that value will also be added into the 25 cm cube of ammonia, because 25 has to be added separately. So this will increase the volume of the ammonia present in the conical flask. So we will write here uh, there will be more than 25 cm cube of ammonia, of aqueous ammonia in conical flask. More than 25 cm cube of aqueous ammonia. The reason is it will have two different portions. One is the ammonia present because of the rinsing, and the other ammonia is that we added separately to make 25 cm cube. Then D says, deduce which solution copper sulfate is more concentrated. Explain your answer. All right. So which one is more concentrated? If I come over here and also I can say this one was 21 cm cube and this one is 9.2 cm cube. Okay, so the difference, what you see, this is the difference of the copper, this is the volume of the copper sulfate added, 17.7 cm cube versus 9.8 cm cube. So let's use the stoichiometric equation here. Sorry, let's use the formula here. N is equal to Cv. This formula is used to calculate the number of the moles. We are supposed to tell which one is more concentrated. The concentrated means we need to know the value of the concentration. C indicates the concentration. So rearrange this equation to find C. So C becomes N over V. Okay, now we do not know the number of moles here because we do not have the concentration value, but we are supposed to find the concentration value. What is C? C has to be determined. We do not know the C value. What is it? C. So we can here, we can however use the values of the volume here. In the experiment number 1, there is 17.7, and in experiment number 2, in experiment 2, we have 11.8 cm cube. So what we see, C is inversely proportional to the volume. If the volume is smaller, then the concentration will be higher. So more high concentration means if there is higher concentration, it means it's concentrated form. It's a concentrated, and that's what question was asking you. It was asking which of the two experiments or which of the two solution A and B is more concentrated with respect to the copper sulfate. So the one which has more C value will be concentrated. So according to the values of the volume, if we say that 11.8 is smaller in volume, it will have more concentrated form of the copper sulfate. So this is solution B. Solution B is more concentrated. So we say solution B is more concentrated, and the reason is that as smaller, because we have to also explain, we have to deduce answer is this, and the explain part is over here. As smaller volume was used or needed. We already saw that in the table. Then next question is, deduce how many times more concentrated this solution of copper sulfate is than that of the other solution of copper sulfate. How many times? Okay, let's use the mathematical way of finding this answer. I will go back to the table and I will see the results here. Over here, one answer is 17.7, the other one is 9.8. So more concentrated is 11.8 and less concentrated is 17.7. In other words, we can also use the results as 17.7 divided by 11.8 divided by 9. 9.8 divided by 11.8 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 11.8. The answer will come out to be 1.5. Why I'm using 17.7 in the top and 11.8 in the bottom? The reason 17.7 has inverse relation with the concentration. If I write this is my C1 and this is my C2, C stands for concentration. I already know that C2 concentration is inversely proportional to V2 and C1 concentration is inversely proportional to V1. That's why I'm using inverse of the values. I'm using the higher value on the top and smaller value in the bottom. So according to this, the C2 value will be greater and it will be greater by 1.5 times. So my answer comes out 1.5. The next part is describe how the reliability of the result obtained can be checked. So the reliability can only be checked if we perform the experiments 1 and 2 multiple times. Just perform these experiments multiple times and the results that you got here, they should be repeated. What I mean to say that you should get similar result like 18.3 again or 18.2 again. Not here. Actually, it is checked over here. The volume added, that matters more because initial and final periods can vary. They can vary in the second experiment, but the value which you get in against the added value, or you could say tighter value, they should not vary. What I mean to say, you should get values exactly the same, or maybe a difference of 0.1 cm cube, that is 17.6 or 17.8. That could be acceptable, but not more than this. And similarly, the values which you are getting in the experiment 2, it should not vary more than 0.1. You can either get 17.7, you should get 11.7 or 11.9, but not more than 11.9 and not less than 11.7. Less than 11.7 and greater than 11.9 will not be acceptable. So what we said, we should repeat the experiment and compare the results. Repeat experiment, repeat experiment and compare results. Then F part says reduce the volume of the solution A required when experiment is carried out with 10 cm cube of the aqueous ammonia. So solution of A required when 10 cm cube was used in experiment number 1. Yes, it is experiment number 1. So if we go back here, it said that it used 25 cm cube of the ammonia. 25 cm cube ammonia was used. And in that situation, the volume in the experiment 1 used or added was 17.7. So I will do the calculations here. Ammonia added was 25 cm cube. And copper sulfate, which is CuSO4, was added was 17.7 cm cube. Now the question says, what if you used the 10 cm cube here? Then how much value of the copper sulfate was obtained, the volume? So simply we are doing the ratio and then you remember the steps I explained in the theory. We do the cross multiplication. So X will be equal to 10 times 17.7 divided by 25. So it is it is equivalent to 7.08, that can be rounded off to 7.1. So let's go back here. You can write 7.1 CMK. Why are we using 7.1? Why not 7.08? Why not this? Because in our in our table of volumes, we have been giving all the values in 1 decimal point. All of these values were 1 decimal point. That's why we used the answer rounded off to 1 decimal point. So this is done. Then G says, give an advantage and disadvantage of using a volumetric pipette instead of merging cylinder. So volumetric pipette, as you know, it is more accurate because the calibrations on the pipette is very smaller, and they also used very precisely for value for volume measurement. So we will say it is more accurate. Also, the percentage error or accuracy of the error is smaller in case of the pipette. Now disadvantage. Now what's the problem of the measuring cylinder here? Sorry, what's the problem of using the pipette here? Pipette, as you remember, it's a long column and it has to be filled using the bubbler at the end of it. We need to do a very precise technique to fill the pipette and then transfer the volume into the flask or in the uh, beaker. This method takes longer. You have to fill the pipette up to the mark. You remember the mark is somewhere here, just below the filler. The mark is somewhere here. This mark must be correctly measured by the value by the volume of the liquid which is going to be taken in the pipette. So this takes longer. It takes longer to do the transfer. However, in the case of the measuring cylinder, which is something like this is the measuring cylinder. Measuring cylinder does not take this thing because there's a widely open mouth, wide mouth, and you can easily transfer any liquid inside of this, and you can easily take out the liquid according to your choice. You can take out the liquid and you can add the liquid in the measuring cylinder very fast. So that's why it doesn't take longer, but accuracy is smaller. So you say slower or takes longer. So in this way, we have also completed the second question. All right, so that's all for today. I will finish this paper in the next class. Till our next class, take care and bye bye.